Hello everyone, my name is Juan Fraire and in this opportunity I will present DtnSim. DtnSim is a simulator of delay tolerant networks, particularly focused on space and particularly focused in routing problems. And I will present a brief introduction of the tool, an overview of its architecture, and we will overview a very simple example of how to use it, how to install it, and how to get results and how to explore different results from simulation. DtnSim was thought to model and to study delay tolerant networks in space. Space implies near-Earth environment, but also deep space. In these two environments, signal delays are very high, and also disruptions happen very often. Therefore, Internet protocols and Internet solutions for data flow cannot be applied directly here, and a different family of protocols and routing solutions has been developed under the name of delay tolerant networks. In delay tolerant networks, data does not longer flow instantaneously end-to-end as done by Internet, but instead, nodes in the network can store data temporarily in order to overcome disruptions and in order to tolerate delays. And for instance, to await from confirmation from next hop, data cannot be deleted locally until this confirmation arrives. So in the end, in DTN, data flows in a store, carry, and forward fashion. And nodes in these networks might have to store data to tolerate delays and disruptions. Particularly in space applications, such as the one described here, the node's trajectory are predictable. So this is quite convenient in order to exploit the information of these time-evolving topologies. And this information can then be used for taking efficient routing decisions. However, routing solutions based in this type of DTNs depends on time. And this is because the topology is time-evolving. This is because data might be received at different moments. Data can be routed at different moments. It can be also sent at different moments. And it will eventually arrive at the destination in different moments as well. And this is something that changes from traditional internet topologies which are considered statics, and data can also be considered instantaneously delivered to the destination. In DTN, the time dimension makes routing decisions a lot more complicated and requires different approaches to study and to optimize routing solutions, which are now dependent on time. So in order to study delay tolerant networks in space, we propose to develop a simulator which objective is to study routing in space DTN. Not only that, but also its immediate consequences such as planning and congestion. In particular, since topology can be predictable and it can be encoded and it can be used by routing solution, planning becomes a particular aspect of space DTN. And also congestion is another big problem in the research area, which is since routing depends on time and links are not always available, congestion can be very difficult to handle because there is not you cannot use feedback information from the neighbor nodes all the time. Therefore, this node can become easily congested, and congestion needs of particular attention to solve, and still a very interesting open research issue in space DTN. An event-driven simulator is required to study scenarios which spans long time periods. Studying space DTN might involve scenarios which can be spanned in several days or even weeks. Therefore, event-driven simulators are required to compress the simulation time and to get results in shorter periods of time. The architecture of DtnSim should be modular. We should be able to exchange different routing and protocols. This is what our object of study is. The interface should be able to interact with existing C code. And this is a very important feature because we want to study routing implementations that are already written in different DTN implementations, such as ION, implemented by JPL at NASA, and MicroPCN, which is a software implemented by Technical University of Dresden in Germany. These are two open source software codes that are open to download and to use it. and we want to DtnSim to interact with these existing codes and routing solutions. Therefore, one of the framework chosen for DtnSim is Omnet because it basically matches these conditions. It's modular, it can interact with existing C-based code, it is an event-driven simulator, and it allows to study efficient routing solution for space DTN. So DtnSim architecture is used in Omnet++, has this aspect, and in DtnSim, nodes are generally implemented and node behavior are described by 3 layers or 3 modules. These 3 modules are named COM from communication, DTN from Delay Tolerant Network, and App from application. In general, from top to bottom, application is the layer in charge of generating traffic and receiving traffic. This is where user application should stand on, and this layer either generates traffic and for a given destination with different settings, and also acts as a receiver in remote nodes. The DTN layer is the layer in charge of routing data and storing data. This is the most important layer on DtnSim, and is where all settings will typically be configured and where new models will be introduced and studied. The communication layer is an abstract model of whichever underlying protocol is modeled. DTN protocol solutions are currently proposed as an overlay layer which can stand on top of any space protocols such as CCSDS protocols, or it can also work over internet protocols such as TCP/IP. Whichever behavior we want to model from these protocols should be implemented in the communications layer. At the moment, the communications layer is practically transparent and it doesn't model any particular effect of the protocol, and all the effort of DtnSim of current version is implemented in the DTN layer. So in order to import DtnSim, we should first of all install Omnet++ IDE, which is accessible on internet to everyone. This Omnet can work on Windows, can work on Linux as well. Once installed, we go to File and then Import. We can import project from Git. We just choose Clone URI. We insert the DtnSim Git repository URI, and we just have our project imported in our Omnet++ interface. Very easy. Once we have the project installed, we will overview a very simple example, which is located in use cases and tutorial, and example 1.ini. Ini files are settings files in Omnet. And in these text-based files is where we configure and we set the settings of the scenario we want to simulate on DtnSim. In this slide, we can see a very simple example, and different parameters are configured. Most importantly, and one of the most relevant of them, is what's called the contact plan. DtnSim has a central node. We can see in the lower left part, we say this DtnSim.central, which is like a manager node of the simulation. This is not a DTN node. We will see that in the next slide. But the central node has like the general parameters that will be used throughout the simulations. And one of the key parameters here is the contact plan. And the contact plan is the expected topology of what the connectivity is going to be like in the simulated network. In this example, contact plan is encoded in a text file, which is included in the contact plan directory within the same tutorial directory. And it is a very simple text-based file, which basically has a contact command, which has 4 or 5 parameters after the command. The first 2 parameters, which is +0 and +100 in this example, are the start time and the end time of a connectivity of a contact, which is an opportunity of communications between node number 1 and node number 2. So these are the first 4 parameters of this line. And the 5th parameter is 1000, which in this case means that this contact or this connection will have a data rate of 1,000 bytes per second. So this is expressed on bytes, and this is a contact plan, and this a series of these commands builds a contact plan which can be used by routing solutions to take efficient routing decisions. And in the case of DtnSim, this contact plan will also be used to establish the connection between the different nodes in the simulator. Another important command which is included in the contact plan is a ranges command. It's very important to have this included, and ranges command models the delay that the distance actually between nodes, in this case number 1 and number 2. So in this example, a range command says that between time 0 and time 100 in seconds, nodes 1 and number 2 will have a range of 0 seconds of light speed. So this means that there is a 0 delay between node number 1 and number 2. In other words, data will flow instantaneously from node number 1 and number 2 within the contacts previously configured in the contact plan. For those familiar with ION implementation, this is exactly the format that ION code uses to describe the contact plan. Further ahead in this initialization file, we can see that the three layers of DtnSim are configured. First of all, DtnSim.nodes number establishes how many nodes we're going to simulate in this scenario. And then for each node, we can establish in the DTN layer which are the routing solutions that we're going to use. In this very simple example, we'll use a direct routing, which means that we will just forward the data to the destinations whenever we have a direct contact with it. So on the application layer settings, we will first of all enable the traffic generation, which is basically enable the application layer. And then we can configure bundle numbers, start time, destination endpoint ID, and size of the packets or bundles that we're going to send. Bundles are essentially packets in the DTN protocols. So in these strings, what we configured is a comma-separated strings, right? Where each element in between commas are different traffic generators. So for instance, in this case, we have 3 traffic generators. The first one generates 3 bundles at time 0 with destination 2 and with size 100. The second generator also generates 3 bundles with start time 10 seconds, destination ID also 2, and with a size of 200 bytes. So this way we can configure several traffic generators in DtnSim. In this case, they're all configured in node 1. And this is a traffic model that the simulator will consider while running the simulation. It's worth noting that communication layer is transparent, and therefore there is no any specific configuration for this layer. As DtnSim evolves, communication layer can start modeling more particular effects such as channel error rates or other aspects that we want to model, and we want to study how they interact with the DTN protocols. So once we have configured our initialization file, we can build and run the scenario directly from the Omnet interface. This is the green play button, which is on the top. Once we hit play, we can manage and track the execution via a TK environment interface, which has also play buttons. We have accelerated execution speed options. We also have a stop. We can stop the simulation, and we can keep track as time advances by keeping track of the time interface. In the interface, we can also see that its nodes are these small nodes with satellite icons in this case. And there is the node ID, and there is black arrows between nodes where contacts are happening at the simulation time. We can see bundle flowing from one node to the other in this case. And we can also keep track of the bundles which are stored in each node by this SDR blue label on top of them, where SDR stands for Spacecraft Data Recorder, which is generally a common name in satellite community to name the storage of each satellite. Once the simulation is completed, results can be explored and can be analyzed or post-processed directly from the Omnet IDE, from the Omnet interface. So a results folder will be created within the same tutorial folder, and within the result folder we can see two types of files, scalar and vectorial files. And by just double-clicking these files, an interface will open, which is an Omnet interface that facilitates the study of these results stored in these files. In particularly, we will be able to see different statistics and vectorial files stored in the application layer and the DTN layer. In the application layer, we can generally study received bundles count and delays also, and send bundle counts. This is basically one of the first graph here we see on the lower left part of the slide, where we have an histogram, for instance, of how many bundles were received and which delay they were received, in this case at node 2, which is the destination of our communication. On the DTN side, we can study the different hop counts in case of nodes of network with several hubs, or how many hubs were revisited, which can be a very interesting metric to study if root loops were occurred during the simulation. Or we can study storage, which is a very important metric in DTN because in contrast with traditional systems, internet systems, DTN is deeply based on storage capabilities in nodes, so it's very important to study. And in this case, we can see in the lower right part of the slide a storage utilization in bytes in node number 1 as time goes by. We can see that as we can clearly see here that the 3 different traffic generators we use in our case, in our simulation case, generates 3 bundles each time, and this increases storage utilization, and as these bundles are transmitted, the storage utilization drops to 0. So we have reviewed a very simple example in order to understand the workflow of the simulator, but several features are also included in DtnSim. We suggest the reader or the user to go and follow other tutorial examples in use cases tutorial folder. Example 2, 3, and 4 introduce several aspects which are very interesting. Example 2, for instance, study contact graph routing solutions. There are 2 settings in this example. The first setting study a general model of CGR, and the second one studied the real CGR implementation in Ion, which is used by an interface that interacts with the C code of this ION software, particularly version 3.5.0, and uses the real Ion software to calculate route in DTN. Example 3 illustrates how batches with parameter settings can be run. These are how we can use console commands and different options to run several simulations with different parametric settings. And example number 2 introduce more complex routing solutions, named CGR Model Revision 17, which are routing solutions with different settings, different options, different route table sizes, etc. Most importantly, we suggest the user to feel free to explore the DtnSim code, particularly in source node DTN routing folder, and to discover and why not modify different routing solutions. This is where most detailed description of routing solutions in space DTN can be found. Also, we suggest the user to study different SQL commands, which can be conveniently coded in Python to post-process results from complex simulation scenario. Some examples from these post-processing tools can be found in utils and result plot folder. And last, we also suggest to study there are different topology outputs that can be obtained from DtnSim, and these are very important when networks are larger than this example we have used here. And with larger, we are not only referring to a large quantity of nodes, but also with very long topological intervals where contacts can become very large, and with very high quantity of contacts can be described a contact plan. To use this output, DtnSim relies on Boost library, which is an optional installation, which is also described in the README file of the DtnSim. And these type of outputs are the one that can be found by using this extension of DtnSim. As we can see here, this is a time evolving graph representation of the simulated networks, where the data flows, different data generators are shown with different arrowed colors, and it's very easy to see how as time goes by. This is from left to right. The network is split in different states, in this case named with the K letter from 2 up to 8. And in each state, represented by a static graph, we can see how much data flows from one node to the other. And it's a very convenient static way of visualizing how a time-evolving traffic flow behaves in a time-evolving topology like the one studies in DTN. So this is like an advanced feature of very important, of highly importance in DtnSim when the user requires to study more complex topological problems. So this is a very quick overview of DtnSim, of a very simple example and only a glance at with advanced features. We suggest the users to explore DtnSim in depth, and also to feel free to contact us via email if there is any specific question that you have. So there is our emails. Thank you for your time, and feel free to contact us and to use DtnSim for your space DTN studies. Thank you for your time.